Welcome to the last lecture by Tom Hutchcroft on uniform spanning forest and high dimension. He'll be lecturing for about an hour with a short break at the halfway point. And I would like to remind you that this lecture is being recorded, and so please turn off your camera if you don't wish to be seen. Let's begin.
Thanks. So let me share my screen. So to remind you what we were doing last time, so we're interested in understanding the past of the uniform spanning forest. So remember, we have this oriented version of the spanning forest, so you should be able to see this here, where every vertex has one arrow pointing out of it and some random number pointing in. And the future of the vertex is when you follow those arrows forward, starting from the vertex, and the past is everything that you are in the future of. So the past of the origin is the set of V such that 0 is the origin is in the future of V. Okay, and one-endedness is equivalent to the past being finite. So what we saw last time is that the past of the origin is always finite when you're in at least 3 dimensions. In fact, it's true in 2 as well, but the proof is different. And we also proved a quantitative bound, saying that the probability that the past survives to n generations, so that you have a path of length n, simple path of length n in the past, is polynomially small in n, with some power that depends on the dimension. Okay, and the way we did this is with the interlacement-Alder-Sproeder algorithm. So remember, the interlacements is this Possum process of double infinite random walk trajectories that we defined as a kind of a limit of random walk excursions on these finite graphs with wide boundary conditions after a Poissonian time change. And the way you compute the forest from the interlacements is for each time t, so which you can choose, you look at the first time each vertex is visited by some trajectory, and then you look at the first edge that trajectory took to get into the vertex, and you include that in the forest, but backwards. Okay, and the theorem says that for each t that you do this with, you get a copy of the wide uniform spanning forest. So in particular, we can change t, and we get a dynamical version of the wide spanning forest, and these dynamics are helpful for analyzing the questions about the past, even though those are static questions. Introducing the dynamics actually makes them easier to understand. Okay, and in particular, we had this picture that the past of the origin sort of can jump when the origin is itself hit by a trajectory, but in between times, as we run time backwards, it gets monotonically smaller. So it can jump up when the origin's hit, otherwise it's getting monotonically smaller, right? And we kind of understand exactly how this works. When a trajectory hits part of your past, the part of the past that it hits, it kind of steals away from you. So everything below that gets cut off. Okay. And so we use this to prove this quantitative version of the one-endedness theorem, where we had this dynamical thing where either the origin gets hit within time epsilon, which has probability epsilon, or it doesn't. And then basically you have to have one of these paths that's there at time epsilon, and it survives between time 0 and epsilon, so it doesn't get hit, right? And this hitting is controlled by the capacity of the path. And just using this sort of deterministic lower bounds on the capacity, we got this n to the minus d minus 2 over d bound. Okay. Now, what we're going to want to do today is to try to improve this and actually get sharp bounds on the same probability. And you can see that the place where we're really losing, or at least one place where we're really losing something in this argument, is that we use this deterministic bound saying that the capacity of any n vertex set is at least n to the d minus 2 over d. And this is a sharp bound, but it's sharp when the set is a ball. Okay, and it's not sharp in the case that the set is a loop-raised random walk, which is really the relevant thing here. Okay, so that's one thing we'll want to revisit and then see how we can take improved control of the capacity of a loop-raised random walk and use it to improve our bounds in this theorem. Okay, so before I go further into that, let me take a step back and talk about the big picture for, high-dimensional critical exponents and so on. So very broadly, the picture is as follows. So if we have some critical statistical mechanics model on a lattice, we generally expect that the sort of interesting large-scale features of it will be described by some critical exponents. Okay, so for example, if we consider instead of the spanning forest a model that will probably be more familiar to many of you, which is percolation. So we expect that in critical percolation, there should be some exponent delta such that the probability that the cluster at the origin has size at least n is roughly n to the minus 1 over delta, up to perhaps some sort of sub-polynomial corrections. Okay. Now, these critical exponents, they're expected to depend on the dimension, but not the fine details of the model, right? This is the prediction of universality. Okay, but there's actually more that you can say than that, which is that the these exponents delta, the critical exponents, so an example being delta, are supposed to stop changing, stop depending on the dimension once you go above some special dimension called the upper critical dimension. Okay, so for percolation, this is 6. For the uniform spanning forest, it's 4. Okay, so for example, for percolation, it's a big theorem of Hara and Slade and follow-up work that this exponent delta is always 2 in high dimensions, right? But in low dimensions, somehow the lattice is constrained enough. There's not enough space for the model to kind of spread out and do what it would really like to. It's being constrained by the lattice in a non-trivial way, and this ends up in these exponents being different. And this is a subtle effect, but it turns out to be the case. Okay, so for example, in percolation, this delta is supposed to be 2 above 6, and then in 2 dimensions you get these weird rational exponents. This is quite typical. In these intermediate dimensions, we really don't know what it is, or that it exists or anything like that. These are all big problems. And then you also get this additional effect, which is that when you are at this upper critical dimension, so 6 in the case of percolation, you expect to get basically the same thing as the high dimensional case, but with some kind of log correction. Okay, and these phenomena are all expected to hold very generally, with maybe different values of exponents, but for all sorts of models, so percolation, Ising, random cluster, uniform spanning tree, etc. As long as the model is undergoing some kind of continuous phase transition, or the uniform spanning tree is sort of a self-critical model, you should kind of always expect roughly this picture. Okay. Except that the upper critical dimension depends on the model. So for the spanning forest, it's 4, not 6. Okay. So the result that I want to tell you about today is a confirmation of the high dimensional part of this picture for the uniform spanning forest. Okay, so in particular, I'm going to focus on this exponent that we've been looking at, but you can look at other things as well. So remember, this is the probability that the past survives for n generations. Okay, so you could imagine that in general dimension, this should be like n to the minus 1 over rho plus little over 1. Say where rho is this exponent that you'd like to compute. Okay, and so this, the first theorem, which is already published, says that you have the mean field behavior that you expect in high dimensions. Okay, so you should compare this to a critical branching process. So the probability that a critical branching process survives for n generations is also of order 1 over n. So it's saying that in high dimensions, the past of the uniform spanning forest basically behaves like a critical branching process, which actually, if you do the wired spanning forest on a tree, so on the three regular tree, the past is actually exactly distributed as a critical branching process. So it's saying that high dimensional lattices, the model behaves in approximately the same way that it does on a tree. Okay. And this more recent ongoing work with Perla Sousi that will hopefully appear fairly soon says that we're also able to compute the logarithmic corrections for the same thing in the upper critical dimension when D is equal to 4. So I'll be able to tell you a bit about how this goes, although there are a lot of this is much more technical actually to get it to work properly than the high dimensional case, and there are a lot of details that I'll have to brush over. So here I'm focusing on this one thing, but there are many other exponents you could look at. For example, the volume of the past, or the probability that the past reaches some distance in ZD, and these are all things that you can understand. Once you understand this, you can kind of derive the other exponents from it. Although in 4 dimensions, it's quite hard. But in high dimensions, it's not so hard, and this knowing one exponent is sort of enough to know all of them. Okay. So a few other things to mention before we get stuck in. So one is that there are some related results about scaling limits of uniform spanning trees. So Perez and Ravel in 2004 in a paper that was actually never published for some reason, but I think it's correct anyway, that proved that if you take the uniform spanning tree of, for example, a big torus in high dimensions, then it converges to the continuum random tree, which is the same thing as the limit of a uniform random tree. And so this is another instance where you get mean field behavior in high dimensions. The model is sort of in a higher dimensional enough setting, the geometry kind of trivializes and the model behaves the same way it does in this geometrically more trivial setting, a tree or a complete graph. Okay. And this result was also extended to the 4-dimensional case by Schweinsberg. So that's much more difficult. And you also have to, there is a difference between the 4 and 5-dimensional case, but it's that the scaling that you have to do is different. You get sort of log corrections, but they don't appear in the scaling limit. They appear in the scaling that you have to do to get that limit. Okay. So these results are, morally closely related to our results, but they're quite different in the detail. Our results sort of apply on a different scale. I mean, our results are sort of more like things about mesoscopic scales on the torus, whereas theirs is really, it's a very global result. So although these two results are morally related to each other, the proofs are very different. Although I should say that ideas from our proof can be relevant for these scaling limit considerations. So in fact, there's a paper plus I think ongoing work by Michele, Macmius and Shalev, where they prove, they studied the diameter of the uniform spanning tree in high dimensions using some of the same ideas we'll be looking at. And this is relevant, for example, if you want to improve the topology with respect to which this convergence holds. So anyway, so there is also stuff about scaling limits, but we won't talk more about that. I'll also say that our analysis in the 4-dimensional case is going to rely heavily on analysis of the 4-dimensional loop raised random walk that was done by Greg Lawler in the 80s and 90s mostly. So I'll talk more about that when we get to it. Okay. So as I said, we're going to want to eventually come back to this proof that we did and see how we can improve upon it once we know something about the capacities of loop raised random walks. What I want to do before that, though, is to come from the other side and talk about how we can prove lower bounds on the probability that the past survive spanning generations. Okay, and 5 dimensions and higher, this is actually very easy using this dynamical picture of the spanning forest that we developed. Okay, so let's try and prove this theorem that says that in high dimensions, d at least 5, the probability of surviving the past surviving to at least 10 generations is at least constant over. Okay, so here's the idea. We want to say that roughly having this past reach generation n, statically, it's kind of the same thing as the dynamical event that the origin is hit in some small window of time. Okay, so first of all, let's just notice that the probability that the origin is hit by a unique trajectory in this window of time is of order 1 over n. So this is just by the definition of Possum. Okay. Now, we also know that from the definitions of interlacements that conditioned on this event that we get a unique trajectory, let's call it W, it basically looks like a doubly infinite random walk, right? So it has this forward part, which is just a random walk, and then it has this backwards part, which is a random walk conditioned not to return to the origin. Okay. Now, we know that in high dimensions, d at least 5, by the theorem of Erdős and Taylor, which let's go back to, that we proved before, that with constant probability, these two parts of the walk of W don't intersect after time 0, right? Because they're just random walks. In high dimensions, they might just not intersect each other. Okay, so this happens with constant probability. Okay. Now, imagine that, so of course, when I compute the forest from the interlacements, I don't just have this trajectory W, I have all the other trajectories as well, right? But the way the algorithm works is that trajectories that arrive earlier have precedence in the algorithm. So that means any trajectory that arrives after time W is, we're going to be able to safely ignore it, basically. So in particular, if W was the only thing in our interlacement process, which of course it isn't, then the past of the origin would be infinite, right? Because we can apply the Albers-Broda algorithm just to W. It doesn't give us a spanning forest, but it gives us a tree, right? We just, every vertex that is hit, we take the first entry edge and we put it backwards, same as before, right? And if we apply this algorithm just to W, we in fact get a two-ended tree. Yeah, so Mark asked a question, does the conditioning make the constant larger? Yes, it does by a coupling argument, because you can, the walk conditioned not to return, you can write it as the, or a walk that isn't conditioned not to return, you can write it as a concatenation of a random loop and then a walk that's conditioned to not to return. So there's a stochastic combination. But anyway, we don't need to know that, we just need to know that this is some positive constant that this happens. So if we just applied the algorithm to W, we get actually a double infinite tree. Okay. So in particular, let's take eta to be an infinite simple path that's in the past of the origin in this tree that we get by applying Albers-Broda to W. Okay, and just to say, eta is going to come from the forward part of W because there's this edge flipping thing in the definition. So it's slightly confusing, but this negative part of W will become the future of the origin in this tree, and the positive part will become the past. Okay. And in fact, one can prove that eta is distributed as a kind of conditioned loop as random walk, but we don't actually need that for this proof. It's just some infinite simple path. Okay. Now, what happens is that the forest F0, it includes all of eta up until the first time that you're hit by some earlier trajectory in the interlacement process, right? Because W has precedence over anything that arrives after it. So in fact, this will be exactly, you'll get exactly this part of eta up until the first time that you're hit before. Okay. Now, by the splitting property of Possum processes, if I just look at the first n steps of eta, right, then the probability that they're not hit by any earlier trajectory is at least this exponential thing, just because all I've conditioned on are the trajectories that hit the origin in this window. So I then have a bunch of other trajectories, but they're just independent of those ones by splitting. So the probability that none of them hit these first n steps, it's just this Poisson thing. So it's a Poisson. The number of them that hit this first n steps is a Poisson process with intensity given by the capacity. I'm looking at it on this interval of length constant over n. Okay. Now, on the other hand, the capacity of any set, so remember this had this definition that it's the sum of the degrees times the escape probability. So in particular, it's always at most the sum of the degrees. So in our setting, degrees are bounded, they're constant. So the capacity of any set is at most a constant times its volume. Okay. So if I just plug that estimate in here, I get that this is bounded by a positive constant. So what we've shown is that in high dimensions, if I condition on this event that the origin is hit by a unique trajectory, in this interval, then the conditional probability that the path reaches level n is actually a positive constant. Okay, and this event that we're conditioning on has probability of order 1 over n, so we get that indeed this probability of surviving to level n is at least 1 over. Okay. Now it turns out that the same strategy actually works to give the correct answer in dimensions 3 and 4 as well, except that it's much harder to analyze because there's a few extra things going on. So, this is no longer true. We don't get non-intersection with constant probability, but we know how this probability depends on n. If I want this, the first n steps of eta not to be hit by the other part of w, I know how that behaves. And also this bounding the capacity linearly is not going to be correct. So it turns out this is actually sharp in high dimensions. The capacity of an n-step loop raised random walk really is of order n. In low dimensions, that's not true anymore. But again, we can understand how it does grow. And if you put all these ingredients together, this bound will actually give you the correct lower bound. And it's not too difficult to do this. An interesting thing to note, though, is that actually these two different effects that I've mentioned, they're actually competing with each other. So one is trying to make the probability smaller and one is trying to make the probability larger. So the fact that in low dimensions, the capacity of the n-step loop raised random walk is growing sublinearly, it basically means I can take epsilon to be larger in this proof. And that's going to help make this probability actually be bigger. On the other hand, this thing that this non-intersection probability now is decaying with n is making it smaller. So you have these two competing effects. And for example, what happens in 4 dimensions, and we'll talk a bit more about this later, is that the capacity is really of order n over log n to the 2/3. But this non-intersection thing is like 1 over log n to the 1/3. So this lower capacity means we can take epsilon a bit bigger in this argument. And what we get is that the probability is at least this term, which is epsilon, times this non-intersection term. Okay, and it turns out that the larger capacity thing wins, and what you get in the end is bigger than in high dimensions. But it's a priori, it's not clear why it should be bigger. Why does this effect beat this effect? And I'll come back to this later because it's a very interesting problem to do this in 3 dimensions. Of course, to do this argument properly, there are a lot more detail that I'm not showing you. In high dimensions, the argument I showed you is really a foolproof. Getting this to work, even given these two ingredients, you need to do some technical stuff to get it to work in 4 dimensions. Okay. So maybe if anyone has any questions, it'd be a good time before we start talking about upper bounds. Okay. So I guess I can I'll continue. Okay, so what we're going to want to do is to try to take this argument that we had last time and then understand more accurately how the capacity is really behaving and try to improve the argument. Okay. So what I'll do to stop writing this probability over and over again, I'm going to find Q of n to be the probability that the past survives to generation n. Okay, and what I want to do is that to prove that in high dimensions, this is bounded by a constant over n. And the way that we'll do this is, so this is kind of a way of avoiding picking up these kind of log terms that we had before that shouldn't really be there, is we'll prove an inductive inequality like this. So we'll prove that the probability of surviving to 2n generations is at most constant over n plus, let's say, a quarter times the probability of surviving to generation n. And this factor of a quarter is not particularly important, but it just has to be, this number has to be smaller than a half, right? And if you can prove a bound of this form, then it just follows by induction that you have this bound. At least you prove it for n of the form 2 to the k, but then this is a decreasing function of n, so you have it for all n. Okay. So let's start by just trying to do what we did before. So again, the idea is going to be that this first term, this constant over n, is going to come from this dynamical event that the origin is hit within a small window, right? Whereas this inductive term is going to come from the other thing where we try to say, if we didn't get hit in the small window, what's the probability that nevertheless we survive to generation 2n? Okay, so we can do exactly the same thing as before. So we'll do a union bound. So either we get hit in the small window, or the following happens. So what we did last time is we just said, or there exists a path, there exists a vertex u, which is at distance at level n at the past at time epsilon, and the path between u and the origin is not hit in between. Right? What we want to do now is slightly more complicated. So we'll look at the number of u that are at level n in the past, but they also lie on a path that goes to level 2n in the past. So which is the same as saying that their path survives to generation n. Okay, so we want that u is one of these vertices, and the portion, this path between the origin and u, is not hit by the interlacement process between time 0 and n. Okay, so it's clear, that if I survive to generation 2n and I'm not hit in this small window, then I must have at least one vertex like this, and I can bound the probability that such a vertex exists by the expected number. Okay. So what we'll do next is we'll try to bound this expectation in terms of, so we'll split it into sort of a term where the these paths have the capacity of the order that we think that they should, and another term where they don't. And so a high capacity term and a low capacity term. Okay, so this guy here, which I've just copied here, so this is just the same thing that was written before. So we can bound this by, first of all, if this path has capacity at least delta n, then we know that, again, these trajectories that arrive between time 0 and epsilon, they're independent of the forest at time epsilon, right? And the hitting probabilities are given by the capacity. So just like before, if the capacity is bigger than delta n, then this probability that they're not hit is at most e to the minus epsilon delta, right? So epsilon is the time interval, this is the intensity of the Possum process. Okay. And then we have to bound the number of points that we have. Now, what we can do, like before, is we can use the mass transport principle. So here we have the expected number of vertices u that are in generation n of the paths of the origin and themselves have paths reaching generation n. But this is in fact just equal to the probability that the path survives to generation n by mass transport. So remember this mass transport before, and it's basically the same argument as here. You just say, well, I transport mass, so I take like f x y is the probability that x's path survives to generation n, and x is in the past of y at generation n. Right? And again, it's the same thing where the mass in is exactly this quantity that we have here, but the mass out is this probability because everything has exactly one thing that's n steps in the future. Okay, so we get that this expectation is exactly q. Okay. So then there's this other term, which is where the sort of the bad thing happens, and this doesn't have the capacity that we think it should. Okay. So again, you can do a mass transport, and you get that this is the same as the probability that the path survives to generation n, and the first n steps of the future have capacity less at most delta. Okay. Now, it's going to be non-trivial to upper bound this, but let's just suppose that we can. So what I'd like to say is that if I pick some small delta, so I kind of expect the capacity is going to be linear in my dimension. So maybe if I pick delta to be very small, then you know, I know that if I don't have this capacity constraint, if I just have this constraint, I get q of n. So maybe if I take that event and I intersect it with this low probability event, I hopefully get an event that has probability much smaller than the original one. Yeah, this is not at all trivial because these events could potentially be very highly correlated with each other. I don't a priori have much way of controlling that. But let's just suppose I could. So in particular, let's imagine I could prove that if delta is sufficiently small, I get a bound of this form. Okay. Then if I put all these things together, I'd get this constant times epsilon term. That's just from the origin being hit at a small time. And then I'd get this high capacity term with this thing coming from the path not being hit in between times. And then I'd finally get this term with the bound that I've just, you know, with my wishful thinking bound. Okay. Now, if I have this, I can conclude, because all I do is I take delta to be small enough that this bound holds, and then I just have to take epsilon to be a big constant over n. In fact, this works, log a over delta. Right, so if I take that, I'll get another 1 over 8 here, so I'll get a quarter in total, which is what I wanted, and then here I'll have some maybe really huge constant over n, but it doesn't matter if this constant is really huge. Okay, so if I can get a bound of this form for this term, then I'll be done. Okay. Now, of course, I've been telling you that high-dimensional loop-arrays random walks have linear capacity, but I haven't proved that, right? So certainly the first thing we'll have to do, if I want to try to complete this proof, is I'll have to actually prove something to you that loop-arrays random walks have high capacity. Okay. So let's do that. Okay, so remember again this definition of the capacity, and that, as we said, there are also many variational formulae for computing the capacity as well. Okay, so we really want to understand capacities of loop-arrays random walks, but let's start with the easier problem of trying to understand the capacity of a simple random walk. Okay, so I'll write x superscript n for the random walk stopped at time n, so the first n steps of the random walk. Now, how does this capacity grow? Well, let's try to see what the capacity is in expectation. So this turns out to be very closely related to the non-intersection probability. So if I take the random walk up to n steps, the capacity will be the sum over the vertices in the random walk, which once you're at least in 3 dimensions is basically going to be the same thing as summing over times, because each vertex is not visited very many times, of the probability that if I start another random walk y, then it doesn't hit the random walk, this other random walk after time 0. Okay. So in particular, in high dimensions, this very easily leads to a proof that the capacity grows linearly in expectation by the Erdős-Taylor theorem again, right? Because we can write, this is actually not really inequality, because there's this issue that really I should sum over the vertices that are that have been visited by the random walk, and here I'm summing over times. But let's ignore this because it's not very important. So we get that the capacity of the random walk is this in expectation. I can think of it, if instead of thinking of this one random walk and then this other random walk coming off it, I can think instead that this is the origin, and I have, one random walk x coming off this way and another random walk z coming off this way. So I have these 3 random walks, x, y, and z, and I want y to not hit the union of these 2 paths, x and z, after time 0, right? So up to some fudging, the expected capacity is the same as this sum, okay? Where x is run for time m and z is run for time n and n minus m, and then we sum over the values of n. Okay. Now, in high dimensions by Erdős-Taylor, I know that this probability is bounded from below by something positive. So I get that the capacity in expectation is growing linearly. Okay. Now, in 4 dimensions, you can also understand what's going on. And it turns out, so this was done by Lawler, and you find that the capacity gets this n over log n thing. In fact, the lower bound of this is quite easy to understand, and I'll come back to this in a minute. In fact, unlike many other things in 3 dimensions where we can't compute exactly what the exponents are, the capacity exponent is actually something we can understand in 3 dimensions. And it's square root. Okay. And in fact, here these results are all just about expectations, but these are really the typical values of the capacity as well. And there are many very strong and precise results to this effect in a series of works by Asselah, Shapiro, and Zuzi. Okay, so let's see an easy argument showing that the lower bounds, in fact, for both 3, 4, and greater than 5 dimensions. At least a sketch of it. Okay, so remember we saw before that there's this variational formula for the capacity, where the reciprocal is this infimum where I have to take a probability measure mu supported on the set, and then I have this Green's function. Okay, so as before, I can always get an upper bound on the reciprocal, which of course is a lower bound on the actual thing, by just taking mu to be the counting measure. Okay, so you get that this is always I had to, this squiggly thing means up to constant because I'm ignoring this degree term. Okay. So in particular, up to some fudging again about the fact that really, well, no, this is exactly true. So the capacity of the random walk is at least the number of vertices it visits squared divided by the sum of Green's functions over pairs of times. Okay. Now again, we know that, in fact, as soon as we're in 3 dimensions, because of transients, the range of the random walk grows linearly. Okay, and so this numerator here is always going to be of order constant times n squared when we're in at least 3 dimensions. And now for the denominator, you can just expand everything out. I mean, this expectation, you just write out all of what it is in terms of transition probabilities, and you get this huge, messy expression. But it's completely elementary. And you can eventually simplify it to get this precise bound. It says that the expectation of this quantity is always at least 2n plus 1 times this sum up to n of n times the return probability, and then plus this other tail term. Okay, and so this is similar to some of these calculations we did when we did the proof of the Erdős-Taylor theorem. Okay, and now we know that the return probabilities are like m to the minus d over 2. Okay, so if we just plug that in here, we can get an upper bound on this expectation, and we compute that it's linear when so in high dimensions these sums are both, this sum is going to be convergent, so we just get this linear thing, and this tail thing is negligible, and then in 4 dimensions we get log coming from this sum, and in 3 dimensions we get square root. So these are just very simple explicit calculations. Okay, but if we take this and then we plug it in here, we see that indeed the capacity, because we have some control of the expectation of this, we can use Jensen, and we get that the capacity of the random walk is at least what I claimed in these 3 cases with good probability. Okay. Well, that's nice, and as I said, this gives you some quite weak control, but you can prove a lot more about the capacity of simple random walk if you want to. But really, we're interested in the capacity of the loop rotor. So how might we understand that? Well, it turns out that actually, in expectation, there's something very nice that happens. So you'll remember when we were discussing P-Mantel's theorem, I mentioned this theorem of Lyons, Perez, and Schramm, which says that on any graph, the probability that an independent random walk and loop-raised random walk intersect is of the same order with some universal constant as just the 2 simple random walks, not intersecting. Okay. Now it turns out you can take basically exactly the same proof and use it to prove a related bound for the capacity. So this is something Perla and I are doing in our paper that's to appear. So it says that it works on any graph, take any transient graph and you take a random walk, starting from some vertex, you run for n steps, and then you loop raise, then in expectation, the capacity of what you get is at least some universal constant times the capacity without the loop ratio. And of course, the other way around, the capacity, the loop ratio is smaller, so it's actually not obvious from the definition I gave, but the capacity is a monotone function. So we trivially have that the left-hand side is bigger than the right-hand side without the constants, but in fact, they're always the same up to this factor of 1/256. Okay, so this is a very nice thing. So at least in expectation, we reduce the problem of computing capacities of loop raised random walks to the simpler problem of simple random walks. Okay. So of course there is this issue though that the time parameterization changes, right? So we're really in what we were doing before, we're really interested in the first n steps of a loop raised random walk, which is not the same thing as the loop ratio of an n-step random walk, right? There's some kind of time change. And in high dimensions, this time change is just going to be kind of multiplication by a constant, but in low dimensions, this is going to be a real serious time change. Okay, so for example, in 4 dimensions, it's a result of Lawler that if you run a random walk for n steps, then its loop ratio will have length typically of order n over log n to the 1/3, and with some concentration, that there's some specific constant times this that it likes to do. Okay. So that means that if we want to compute the capacity of the first n steps of a loop raised random walk, that should roughly be the same thing as the capacity of the loop ratio of a simple random walk, but run to time n log n to the 1/3. Okay, so if you plug in what we know, you get that this should be of order log n to the 2/3 over n, and this is not a rigorous argument, but this does actually give the right answer, and it's one of the things we have to do in our paper is to actually make this to do a precise argument to this fact. Okay. And in fact, we also proved that this really holds not just in expectation, but with high probability. Again, these things get kind of technical, but intuitively, everything that you want to work works. Okay. So, okay, now, so let's say we now understand that at least in high dimensions, the capacity of the n-step loop raised random walk is order n with high probability. There's still a problem because this thing that we wanted to analyze before, let's see if I can get the other page of the file. Right, we had this last term coming from when the capacity was smaller than we wanted it to be. So we've argued, at least vaguely, that this second event that we're intersecting with should have low probability when delta is small. Okay, but we still have a problem that we want to estimate the probability of an intersection of 2 events, and they're not independent. Okay? If they were, we could just take delta to be sufficiently small that this second event had probability at most 1/8, and then we'd be done. Okay, but they're not. Now, one situation in which this wouldn't be a problem is if we just had some kind of strong concentration for the capacity of the n-step loop raised random walk. So, for example, if we knew there was some constant delta such that the probability of this having small capacity was much smaller than 1/n, say, then we could just ignore this first constraint and just use this, and we'd be fine. Okay, and this should actually work in very high dimensions. It might work in 5 dimensions. I'm not really sure. seem to remember convincing myself years ago that it doesn't work in 5 dimensions, but I'm no longer convinced. I forgot how I convinced myself. So in any case, this should work in very high dimensions. It's unclear whether it's going to work in 5 dimensions because although this is sort of concentrated, the bounds tend to be not super great because basically the loop raised random walk is not so well behaved. Okay. So how are we going to get around this? So one way we could try to argue, which is actually what we have to do in 4 dimensions, is just to try to argue that these 2 events are approximately independent. And intuitively, it's plausible that they are because there is some interaction certainly between the past and the future, but the interaction probably happens kind of near the origin, whereas you can get all the capacity you want just by looking far away from the origin, say between times n over 2 and n, and this should be roughly independent of what's going on in the past. And in 4 dimensions, we did have to do it this way, and you can make it work, but it's not that easy. In high dimensions, though, there's a trick that gets around this, and you actually learn more by doing it this way as well. So, and this trick is using what's called the WSFO, or what I've been calling the V-wired uniform spanning curve. So, doing it this way will actually give us stronger results than doing it the other way. So this is a variation on the wired uniform spanning forest model that was introduced by Yarai and Reddick. And they introduced it in the context of their work on the abelian sandpile model. And actually, if you want to understand the sandpiles, this other model is often more relevant than the original, the normal wired uniform spanning forest model. So the way it works, remember before that when we defined the spanning forest, we had this graph GN star, right? Where we, let's see if I can find it, where we took everything outside. We have an exhaustion of our vertex set by finite sets, and then at each stage, we take everything outside of Vn and contract it down to this one big vertex delta. Okay. So in this alternative model, the V-wired uniform spanning forest, we fix some vertex V, and we kind of wire V to infinity. So at every stage of the exhaustion, we identify this special vertex V with the bounded vertex. Okay, and then as before, we take a weak limit of, this should have V though, of these uniform spanning trees on these funny graphs, oriented towards the special boundary vertex, which is now identified with V. Okay, so fine. Why is this useful to us? Well, it turns out that there's this very useful stochastic domination property between the usual wide spanning forest and the V-wide spanning forest. So this is essentially due to Lyons, Morris, and Tran. So what this says is, suppose I take the wide spanning forest, in fact it works for this V-wide spanning forest as well, and I take some list of vertex U1 to UK. And imagine that I condition on the futures of all of these vertices. So maybe U1 and U2 are in the same component here, U3 is in the same component. Okay. And now, given all this information that I've conditioned on, I pick some other vertex, say X, which could be the same as one of these guys. Then what this statement says is that conditional on all this blue stuff that I revealed, the part of the past of X, which does not belong to the revealed tree, is stochastically dominated by the component of X in this X wired spanning forest. Okay, so here, that thing is here. So this part of the past, which is kind of hanging off the revealed part of the tree. Okay, so in particular, this the V-wired forest will have this special component at V. It's not a translation variant model. And this special component will actually be finite. So the whole component of V in the V wide spanning forest is sort of like the past of V in the normal spanning forest. And this stochastic domination property is very useful. And roughly speaking, we often use it in a similar way to how one would use the BK inequality in percolation. So if you're familiar with percolation, that's often how the stochastic domination will be used. So one consequence of the stochastic domination property is that so just a very simple case of the thing is that the past of the origin in the wide spanning forest is stochastically dominated by the entire component of the origin in the origin in this modified model. Okay. So in particular, if we define Q0 of n to be the probability of surviving to generation n in the modified model, then it's bigger than the original Q of n, which was the probability of surviving to generation n in the original model. Okay. Now, this is all well and good, but if maybe this new model I've introduced, I don't have any tools for it anymore. I had all these special tools available to me. That's not the case. So, in fact, everything that we know about the usual model has an analog for this other model. So, for example, Wilson's algorithm is basically exactly the same, except you root it at V. But V and infinity are the same. So you start the forest with just the vertex V and no edges, and then you run your random walks, and maybe they hit V, in which case you stop them. Otherwise, they run forever. And otherwise, you just run Wilson's algorithm exactly the same way, but you have this special kind of sync vertex V. Okay. Similarly, you can define a V-wired version of the interlacements. Again, you can define it through this limiting procedure where you consider random walks on this graph Gn star V, and you do your Poissonian time changes and so on, and you get something which is very similar to the normal interlacement process, except it has some extra things. So instead of all the trajectories being doubly infinite, instead you'll get some doubly infinite trajectories that don't hit V. Otherwise, you get singly infinite trajectories of both kinds. So either starting at infinity and hitting V, or starting at V and going to infinity. Or you can have finite trajectories that both start and end at the special vertex V. And again, all these things are sort of the same if you're willing to say V is infinity. Okay. But otherwise, these are actually quite small differences, and generally things work in basically the same way as before. So what you can try to do is to directly analyze this modified model instead of the original one. Okay, and that will give you a stronger result because of the stochastic domination. But we'll be able to use this stochastic domination property, similarly to the BK inequality, to decorrelate things for free. Okay. So if we try and do it before, now I'm using all these modified interlacement processes and so on, but it's all basically the same. So I get this first term from the origin being hit at a small time. Then I get this other term, which is the same as before, except everything here is now this new modified version of the model. Okay, so I need to have a vertex U that's on the past at generation n, and then you have another vertex generation n into its past, and I also need it to be not hit in between. So as before, I can split this into these two terms, the high capacity term and the low capacity term, right? And the point is, whenever I see this event that U has a large past, well, I know that conditioned on the future of U, the past is stochastically dominated by this U-wired uniform spanning forest, right? So it means I can just, using stochastic domination, I can pull out a factor Q0. Again, I can do this in both the high capacity terms and the low capacity terms. Okay, so if I pull it out here, I keep this this capacity coming from the dynamics and this term coming from the dynamics, and I get the expected number of vertices in generation n of the path of the origin. And similarly, I can do the same thing here, but I get this other term with the small capacity constraint. Okay. Now, if I had this bound in the original model, I'd be good because I could do mass transport and I could turn this into a question about loop raised random walk that I already understand. But unfortunately, there's a new problem that emerges, is that this new model that we've introduced is not translation invariant, so we can't use the mass transport principle. Or at least not in the way that we'd like to. So I'm out of time to explain how to do it, but this turns out to be a tractable problem. These two terms that we have here, although they're defined in terms of this funny new model, you can reduce them to questions about loop raised random walk using Wilson's algorithm. And again, it will just boil down to the fact that in high dimensions, an n-step loop raised random walk came from a random walk that also had length 4 n. Okay, so I don't have time to get into details, but these are problems that can be overcome without too much difficulty, and we get that this expectation, just the number of vertices that are in generation n of the past. In the original model, this was exactly equal to 1. In the modified model, in high dimensions, it's at most a constant. Similarly, this low capacity term, in the original model, it was just the probability that the loop raised random walk had low capacity, which is decaying, right? Here it's not, but you can make it work, and you get that it's a small constant. So if you put all these things together, you get exactly this inductive inequality that we wanted to do. Okay. So I'm already slightly over time, but let me talk a bit about some problems so that you'll maybe be able to get something out of all the things you've learned. So as we saw in this proof, passing to this modified model, the V-wired uniform spanning price, it gave us this stochastic domination. It let us basically decorrelate things for free. Now, you can still do that in low dimensions, but the problem is that it's not going to be sharp anymore. And the reason is that in high dimensions, these two probabilities, the probability of reaching the two models, the probability of reaching generation n is of the same order in both. So bounding, one by the other, I didn't lose anything. But in fact, this is not true anymore in 4 dimensions and below. So, for example, what happens in 4 dimensions, it's not so bad. They're only different by a log. But the logarithmic correction is different. So in the real model, you get log n to the 1/3, but in this modified model, you get a bigger power of log. Okay. But this problem actually becomes much worse as you go into lower dimensions. So in 3 dimensions, these two different models actually have different critical exponents associated to them. And in 2 dimensions, this wired model just becomes completely degenerate, and it's actually just the whole, this probability is actually 1 in 2 dimensions for all n. It doesn't decay. So that's very bad. So this technique sort of breaks down more and more as you go into lower dimensions, and you have to really be able to understand how these things decorrelate instead of using the stochastic domination property. One interesting thing, though, is that, as I said, Yara and Reddick, they introduced this modified model in their work on the abelian sandpile model. So I don't have much time to say what that is, but it's a model where you have these random avalanches, and they showed that the distribution of the avalanche at the origin it's not quite stochastic domination, in fact, but it basically is stochastic domination, so let's just pretend it is. It's stochastically dominated from above by the components of the origin in this modified model, the origin wired spanning forest, and from below by the past of the origin in the wired spanning forest. Okay? So what happens is that in high dimensions, these two things actually have the same behavior. So, you know, if you don't care about constants and you just want to determine critical exponents, you can actually get exactly the right, you can exactly understand what the exponents are for the sandpile by understanding both of these models. What happens though is that, if, for example, in 4 dimensions, we don't know how to compute the logarithmic correction for the sandpile model because we just know that it's bounded between the log correction for this model and the log correction for this model, but they're not the same. So a new idea is needed to get the correct thing. And in 3 dimensions, the problem becomes even worse in that these two things have different critical exponents. So you no longer can get the exponents. And in 2 dimensions, this upper bound becomes completely degenerate and you don't learn anything. So figuring out how to close this gap would be very interesting. In 4 dimensions, you only have to close the gap by a cube root of log. Seems like something that might be attainable. I mean, it's quite a small thing. A related problem is that that I think is super interesting is whether you always have this mean field lower bound. So if I ask what's the probability that the path survives to generation n, my conjecture is that this is at least a constant over n for zd in every dimension. And in fact, it's only really open in 3 dimensions, but the hope would be that maybe there's a general argument that shows that this is always true, and then you would learn some interesting things about 3-dimensional loop-based random walks and spanning forests without actually having to do things that are specific to 3 dimensions and therefore might be very hard. So if you were able to prove this conjecture, you would learn that the Hausdorff dimension beta of the 3D loop-based random walk is at least 3/2. And numerically, it's about 1.6, and the rigorous upper bound of Lawler is quite good, but the lower bound is not. And you know, there's not any specific number bigger than 1, which is that the argument is ineffective. It doesn't give any specific number bigger than 1. So if you prove this conjecture, you get 3/2, which is actually quite good. And just to say that what is true is that this origin wired version is always at least constant over n. And this actually follows by basically the same thing I showed you before, the proof of the lower bound. Here you don't have this issue with the non-intersection because you just have one random walk. Okay, so I'm over time, so let me end there, and thanks everyone for sticking all the way to the end.
Right, thanks, Tom. Since this is the final lecture of WOOPS, I would like to take some time to mention the people and organizers who supported us. Specifically, we received support from CRM at Montreal, BURS, PIMS, SMS at Montreal, and MSRI. And we would also like to thank all the other organizers and the speakers who gave really wonderful lectures, and participants who participated enthusiastically. I would also like to thank Ricardo from CRM and Brent Jake from BURS, who provided technical support with Zoom and also making the recorded lectures available online. Okay, so let us also thank Tom Hutchcroft for his lectures. Sarai, can you unmute us so that we could give a round of applause for Tom? All right, I think we should be able to.
Thanks again to all the organisers for inviting me to give this course as well. It's been very nice.